Good evening, everyone. So, in the last lecture of this series, today we will start with the finite element method for parabolic PDs. Then do its prior error estimate, or you can say stability estimates, and then try to give the brief idea of the error estimate in semi-discrete form, and then we will move to the differential quadrature method for elliptic and parabolic PDs in 1D and 2D, and try to explain how to apply the differential quadrature method for parabolic and elliptic PDs and how to find the solution of the equation using differential quadrature methods. So now start again the finite element method for parabolic PDs. So finite element method for parabolic PDs. So let's consider the general form of parabolic PDs. Parabolic PDs of the form ut plus L of u is equal to fx. X belongs to some domain and t is greater than 0 here. So say this is equation number 1. This is equation number 1 where this is omega is the bounded and nice domain, bounded, and you can just write here the smooth domain. Smooth domain of you can say the omega is subset of Rd and d is equal to 1, 2 and 3 here. So f this okay, you can write f of t also here, including f is depend upon is a given function. So this is general form. So, but we will start this equation parabolic PD with the simplest form, and because L is what, and L is the differential operator. So differential operator may be changed here. So it may be the just Laplacian or biharmonic operator, or maybe something. So, but here we will do the finite element analysis for simple Laplacian one. So I am considering here the simplest form of equation number 1. For simplicity, consider 1 as ut plus del u is equal to f. Just I am considering L is equal to the Laplacian operator. This and x belong to the given domain and t greater than 0. Obviously that this equation has some initial condition and boundary condition. So because time, one more variable come here as compared to elliptic PD. So that is the t. So in term there will be some initial condition. So I am saying this, its name, suppose I am saying u naught of x, and obviously the boundary condition, so you say u is equal to 0 on the boundary of this. So this is equation number 2, and say its initial condition, this is initial condition, say this is 3, and these are the boundary condition, means u is 0 over the boundary. So this become number 4. So now before this to make its weak form, as we in last lecture we make many weak forms for different type of elliptic PDEs. So now the same thing here is also used for the weak form. But before that, because this is a time dependent PDE, so we have to define the Bochner spaces, not the simple spaces here, because Bochner spaces are depend upon the T also. So I am defining Bochner spaces. So these spaces are defined upon for let uxt is some function which belong to be a function, x belong to this domain, and t is belong to some interval. Suppose I am saying capital 0 to t, or you can write open interval. There is no problem because at t is equal to 0 solution is given, or you can write this semi-close also. There is no problem because this means at t is equal to 0, the solution of this problem is given here, that is u0. We have to find the solution of this problem inside this interval. So you can include capital T, or you can exclude. There is no problem. So here LQ space are defined this type of, suppose I am taking here just open interval. So here, because u is a function containing two variables x and t, so this is the, because this contains two variables t and x, this is for t, and suppose this is w k p omega. This means this because u has two variables x and t, so this is for t, this is for the space variable, and w k p, you know already the Sobolev spaces, Sobolev spaces. Okay, so this can be defined as, means this type of function, this type of space can be defined in this way. U is some function from 0 to t to wkp. So these spaces means this what we are doing here, we are fixing t from this interval and sending the function into this space, because for when you will fix this t, so this will come into the Sobolev spaces, and such that what is the condition here, such that u is measurable function, and the norm and the integral 0 to capital T norm of this function over wkp and dt is less than infinity. So this is LQ defined here, and obviously with the norm over here, if you define norm over here, so norm will be defined as norm of u over the LQ 0 to t wkp, and this is equal to 0 to capital T norm of u power q and total power 1 by q here, and obviously that dt also here is wkp and dt here. So this is the norm over the, so under this norm, these become the Banach space and then Hilbert space for some particular value of this q. So now these are the our Bochner spaces which are used for the time dependent PD. Okay. So now come to the point. The first thing is that to make the weak formulation of the equation number 2. Weak formulation. Weak formulation again, as we explained in the last lecture, multiply by some nice test function from d omega and integrate over the domain. So we have here obviously you can see that our space is what, because at boundary u is equal to 0, so our space here capital V will be h0 1, because when you will make the weak form, forward this and remember this del u is equal to f elliptic PD. Yesterday we show that the maximum space for the solution where solution of this equation exists is the h01. So same here, just one variable extra here. So let v belong to h01 is the test function, and multiply by v to equation 2 and integrate over the domain, and integrate over the domain we have. So what we have integrate over the domain ut vt dx and plus integral over the domain del u v dx equal to integral over this v and dx for all v belong to h0. Okay, so now this is okay because we can't do anything here, but here in the second term we can apply the Green divergence theorem. So divergence theorem we are considering formula. So when you will apply our Green divergence theorem here, so this will convert it into, yesterday I also explained how to this because this term is equal to, this term become it's like to similar to the integrate by part type. So this become integral over the boundary, so this become del u by del eta into v and ds, and the minus integral over the domain del u dot del v and dx, and due to, because v comes from h01. h01 is what, where where the functions are 0 at the boundary. So this is boundary, so due to this become 0 here. So this term becomes 0. So only this contain this one. So this imply applying this is equal to this. So this become. So finally you get this one, integral over this domain utv dx, and this become minus of this. So this is del u del v dx and is equal to integral over this and this. So we have this one. So or you can write this as utv, because this is the inner product, and minus del u del v and equal to f of v for all v belong to h01. So this is what, this is with initial condition, obviously that this is time dependent problem. So initial condition is there. So initial condition u of 0 is v is equal to, so this is the, you can say its value is given here, just u naught. So with you can say with initial condition. Okay, so now our problem becomes, so we reach 2, 3, 4. Say this is 5. Say this is 5, and say this is 6. Okay, just I am writing this for simplicity. Means in place of x and t, I am saying just ut. For simplicity, I am writing this. This is no problem. Means that for fixed t, this is going into the Sobolev space WKP. So now, what we have done, we have convert our this problem into a new problem, and in this problem, our solution just u and v comes from h01. Okay. So now we will prove the solution of this problem exists or no, means that because we convert original problem into a new problem, that is this is called, you can say this is called the weak form, this is called weak form of 1, sorry, of 2. So this is a weak form. So now to prove the well-posedness of equation number 5, so we have to prove the existence and uniqueness of the solution of this equation. So we will use here to prove this existence and uniqueness diagonalization method. Diagonalization method for existence and uniqueness, for the existence of the solution of 5. So what is that? You can say a step towards the existence, you can say that. Okay, so now attach equation 2, now attach 2 with an eigenvalue problem. What is that eigenvalue problem? As eigenvalue problem as minus del V equal to lambda V, and V is equal to 0 over the boundary, and x belong to the same domain, and x belong to over the boundary here. So I am saying that we are connecting our problem to with equation number 7, which is called the eigenvalue problem. Okay, so now because here this this operator minus del operator is self-adjoint and positive definite, so it has number of countable number of eigenvalues and corresponding eigenvector. This is proved by the Sobolev theory by book by case 1, book by case 1. Okay, so what we get by the proof of this minus del operator is the positive definite, since I can say since minus this operator is self-adjoint and the positive definite, then it has countable number of eigenvalues, numbers of eigenvalues. Say I am saying that eigenvalues are 0 less than lambda less than equal to lambda, and so lambda I, and so, and corresponding, obviously that if you have the eigenvalues, so you can say, or that is lambda I is equal to 1 to infinity type. So countable number of, and what is the condition here? This is the lambda I goes to infinity as I goes to infinity. So you can see this proof is in this book, case 1 book. So, and I'm saying that let phi i's are the corresponding eigenvector which are orthonormal, corresponding orthonormal eigenvectors. That is, means that if these are the eigenvectors, so obviously that these eigenvectors will satisfy this equation number 7. That is, you can say that minus del of phi I is equal to lambda I, phi I for all I, and phi I are 0 on the boundary here. So if we have these eigenfunctions, eigenvectors, so these are obviously these are the eigenfunctions. Okay, because these are some functions, so phi i's are the eigenfunctions. Because the solution of this are the functions. So corresponding eigen, you can say in place of eigenvector, you can say functions here. Okay, so and these are the basis of this V, capital V. Here, what is our V? Our V is this x01. Obviously, phi i's I equal to 1 to n are the basis of capital V, that is equal to h01. And if these are the bases and solution become to belong to h01, so solution belong to h01 and u belong to h01, then because these are the bases, so we can write solution in terms of these eigenfunctions. Some constant alpha i's of t I am saying, and phi I of x. Understand? So solution can be, so I am saying this is the star here, because this u belong to h01 and the basis of h01s are phi i's, so we can write this solution in the linear combination of these phi i's. Okay, so where alpha is t is unknown here. Okay, so these are unknown parameters depend upon the time t. Okay, so now, and this you can find out because obviously because phi i's are what? Phi i's are orthonormal. So take inner product with respect to phi j both sides. So from here you can find easily alpha i's are, means if you will take the inner product u phi j. Okay, I'm writing there. Just so means that alpha i's can be computed with the help of Fourier series analysis. You can say take inner product both sides with respect to phi j. So this become, you can say u phi j is equal to alpha. If you want to take alpha I, so this is okay, because when this I equal to 0, so you can say alpha j here also. Because due to orthonormality, because phi j have orthonormality, when you will take inner product with respect to phi j, when I equal to j, this become 1, otherwise 0. So these are, you can say, the Fourier coefficient, you can say Fourier coefficient. This comes from the Fourier series. I am not going in detail of Fourier series. You already know what is Fourier series and how to find this. So now choose, come to the our weak form here. Choose V is equal to phi I, because this hold for all V belong to H01 and the basis of H01 are phi i's. So choose V is equal to phi I in 5. Choose V is equal to phi I in 5. We have, so this become ut phi I minus del u del phi I equal to f and phi, and t is what? T is greater than 0. Now this term can be a little bit simplifies. This can be written as, you can say, as if I'm going number, so its number is what? Say its number is 7 and this is 8. So now this term can be simplified like that, is equal to, because you can apply the again the integration by parts and apply this one. Phi I is also 0, so at boundary, so this become u and minus del of phi. Okay, and that is equal to what? That del phi I is equal to minus del phi I is equal to lambda I phi I. So this become, lambda is taken the outside because these are the constant, and this become phi. Means that the value of, say this is double star here, the value of this term can be written as lambda is u phi I. So put double star in 8. Put double star in 8. We get ut phi I, and this is minus here, so this minus, you can say it's okay, minus is also minus this become plus, because its value is this one, so I think it should be so it should be plus here. What we have just in it, but we have considered our problem. Oh, sorry, actually our problem was initially minus del u is equal to f. Okay, so not plus here, not plus here. I think I have written plus here, so it is minus here. So that's why this become plus. Okay, when you will apply here, so this become plus. So this is our original problem, ut minus del u is equal to f. So due to after weak formulation, this become positive here, this become positive, and this become positive. So its value is this one. So this is positive. Now fine. So lambda I u of phi I is equal to f phi I. Okay, so here I can say with when put this solution star here and here. Now put say its number is 9 and this is star. Put star in 9. We get, when you will put here, this is the u, so this is the ut. So this means when you will differentiate this with respect to t, so this will become differentiate here. So this becomes summation I equal to 1 to n, and inside will be d alpha I by dt, and this is so I have used here, so you can say this is phi I become, so either you can write phi I is the statistical lambda I, so otherwise phi I here, and plus lambda I, and this I am putting here u again, so this is, you can say, the, if you want to take this summation total, so here this become alpha I, phi I and phi I here, so is equal to, for simplicity I am writing this as phi I. This is just divided by phi I. Okay, so now, so when because this is taken, you can take out and take the inner product of phi I is equal to 1. Yeah, you can say when both are equal, so it is 1, otherwise 0. The same here. So this can become d alpha y dt plus lambda I, and alpha is also here, alpha I, and equal to fi. So this is our problem now with initial condition. initial condition, if you will take the from here, this initial condition, V is phi I and V0 is U0 is what? U0 you can take from here, T is equal to 0, L phi of 0, and take another, because V is also here, so taking a product, so L phi 0 is equal to, so you can say alpha i's of 0 is equal to this one. So I am just giving its name U 0I. This so simple notation I am saying. Okay, so now the solution of this problem is easy to find, because this is what? This is a system of first order OD in the alphas, and you can say by Picard theorem its solution exists and it is unique because that satisfies all the things of the Picard theorem. Picard's theorem says that if we have some problem du by dt is equal to f, if this function f is Lipschitz continuous, f is continuous and bounded and satisfies the Lipschitz condition, then this problem has solution, and that solution is the unique over locally. Okay, so I will apply here, so we can find the solution of this. So the solution of this is what? This is initial value problem. The solution of okay, you can give its name here. Say this is 10 of 10 by, there is a method, variation of constant method is given by you can write alpha I of t is equal to, obviously this alpha is dependent upon the time t, so this become, and after applying the initial condition alpha i's, so this become e to the power minus lambda I of t, and plus 0 to t integral e to the power minus lambda I t minus s and fi of s and ds. So this is the solution of equation number 10, because our motive was to find the solution star. So if we have alpha i's, phi i's are already given to us, because these are the basis functions known to us, so put here, so this will be the solution of our problem. Okay, so means that by this method, you can say the diagonalization method, we have proved that the solution of our weak form exists, and that is unique, and we take help of Picard's theorem for this, and finally you can write, if you will put 11 in star, so you can get the solution, or that is equal to u of xt equal to, it is in summation form, I equal to, okay, what I have written, I equal to 1 to n, 1 to, sorry, this will be 1 to infinity, because these bases are infinite, so obviously these are the infinite one here. So when you will take infinite here, so only will be, only one comes when both are equal, otherwise this become 0. So now, so this become alpha i's, and here is phi I, so you can write its solution like this, summation I equal to 0 to infinity, alpha is equal to this, and this is the alpha I, and just multiply by here phi I, so you will get solution. Okay, so now come to the second step here, the semi-discretization of the problem. Semi-discretization of the problem, because till now we have equation number 5 is the, I think equation number 5, yeah, equation number 5 is the weak form, and that is the continuous one. So now we will semi-discretize the problem, and that semi-discrete will be in the in the space direction. And finally, we can apply the fully discretization, and in fully discrete form, we will discretize the time derivative also by using some stable either finite difference, and some people use backward difference, and some people use forward, and some use Crank-Nicolson also. So stable as you like. So that is with the fully discrete form. Okay, so in semi-discretization problem, choose, because this was at 0, 1, the space. Okay, V is our at 0, 1, and that is the infinite dimensions of space. So to find the solution of the problem, we cannot find solution over the infinite dimensional. So we apply the we have to take our problem to the finite dimensional problem, finite dimensional space. So choose VH subset of V at 0, 1, a finite dimensional subspace. So here will be what? Our problem will become find UH belong to capital VH such that UH, okay, T V plus del UH del V is equal to f of V for all V belong to, oh sorry, not at 0, 1 of V's. So now our problem now reduced to here. So I can say its name, you can say its name is with initial data, obviously that, and T is greater than equal to 0. So as UH of 0 is equal to U0 H. Okay, is the approximation. This is approximation. So say its name, you can say total, you can give its name is 12. Up to 11 we have used here. So this is the 12th equation. So now again, obviously this is finite dimensional subspace. So it has the bases which are finite. So I can choose again, choose if phi I is equal to 1 to, suppose I am saying the capital NH, NH is just notation because I am saying that capital VH is the subspace. Okay, so R basis of VH, then the solution UH xt can be written in the linear combination of these bases. Phi of x. So suppose this is the 13. Again, when you will put this 13 in 12, so this become a matrix form because this is the finite dimensional. So it is easy to write its matrix, and then we can but not necessarily these bases, these phi i's are the previous one, because previous one are the solution of the eigenvalue problem, and that are the orthonormal. So these are just simple basis of VH, and so this can be put 13 in 12. We have, so we have when we will put this and choose here, and choose V is equal to, okay, put this, and one more thing, and choose V is equal to phi j. We have now what we got. It is easy to implement here. So you will put this here, phi I here and phi j here, and here the phi I, phi j. So this can be written in this form: summation I equal to 1 to nh, and alpha, I am writing alpha dash. That means derivative, because when you will put this here as previous, so derivative of alpha will come here, and this is phi I, phi j, and the second term will give alpha I del of phi I del of phi j, and is equal to f of phi j. So similarly, this the initial data can be computed with the help of this. Means when you will put t is equal to 0, so u 0h is equal to alpha is of phi I 0. So I'm just simplicity, I'm saying that u 0h is equal to, this is just alpha is. Okay, alpha is of 0. Sorry, alpha is of 0. So now this can be written in matrix form, because this is a matrix, this is also a matrix, and this is some vector here. So this system can be written in the matrix form. In the matrix form, this can be written as capital A alpha dash of t, because this alpha dash t is also a vector that contains alpha 1, alpha 2, alpha nh, and say this is B matrix. Say I'm saying this is A matrix, this is the B matrix, B of alpha, or that is equal to capital F. I'm saying suppose this is the capital F, where you can write where A equal to inner product of phi I, phi j, and B is equal to del phi j, and F is equal to F and phi j. These are three inner product. When you will put I is equal to 1, j is equal to 1, you will get the first element of this. So it means that phi I1, I2, phi I, j is running, so phi 1, phi 2, 3, 4 and so on. So you can make these matrix. Okay. So if you will use the Lagrange interpolation here, so that's just easy. Calculate this at this small level. These are already calculated, so no need to do the calculation. 1 minus 1 minus 1, like that. Okay. So here, this is our I'm saying some initial data like this. So you can see, because alpha of 0, suppose I'm saying some beta is, here you can say beta of this. So now this system is what? System of ODs, and obviously that this matrix will be the invertible. A will be the invertible, because this become positive definite matrix. If you will see, you will use the Lagrange interpolation. So this matrix will become positive definite. So its inverse exists. So this can be written as this, implying take inverse both sides. So alpha dash of t plus A inverse B alpha, and is equal to A inverse F. So this is a system of equation. So again you can find its solution. Okay. If I say by using finite element method, so again you are here you have to apply some finite difference scheme. Then either you can use forward difference, either you can use backward, or either you can use Crank-Nicolson scheme. So generally people use backward one is enough, because that is the unconditionally stable, and then this system will convert it into a system of linear equation, because totally this is linear equation, and then that linear system is solved with the help of some another numerical method for solving the system of linear equation. For example, Gauss elimination, LU decomposition, or Gauss seidel, like that. Okay, so now this was about the semi-discretization here. So what we have done now, we have semi-discretize here. So, okay, say this is the, so this was 12. Here, UH is the solution of this problem, and U was the solution of this problem, UT plus del U del V is equal to FV of continuous one. So this was continuous problem, and this is the semi-discrete problem. So basically that there will be some estimate over the solution of this, means that this solution is stable or not stable. So I will prove two results for stability of this one, and that is called energy error estimate. So energy error estimate. So, or you can say stability of stability analysis of semi-discrete solution. What is that? That solution is UH. So I will find some bound of this solution and say that this solution is stable. Okay, so in different norm. So first is energy norm. In first energy norm, that is defined by this is triple standing line, triple this phi of t. Phi is some function. So I am defining here what is the first energy norm, that is equal to norm of phi t and phi t square plus 0 to t, 0 to t norm of del phi square and ds, and t is greater than or equal to 0. Say its name is this is 12, 13 up to that is 14. If you want to say this is 14 here, so they say this is 15 if you want to continue in this way. Okay, so theorem is what? What is the theorem? First theorem for the stability analysis of this one. The semi-discrete solution UH of 12, this is a 12, of 12 is stable, or you can say that is it's stable. Okay, with respect, you can say with respect to first energy norm. First energy norm, in the sense that triple standing line UH of T is less than equal to norm of UH 0 plus twice time 0 to T F of S and ds T is 0. We can say that this theorem says that this solution means that first energy norm of this semi-discrete solution is bounded by this one. This means if our if our f of the original problem, our original problem was what? This was our original problem, and u of 0 is equal to some u0, means that if, because this comes from the initial data here, if our initial data and this given function are nice guy, then we can say that this is our stable. Okay, but if these are fs and the initial data is unbounded type of things, then this become unstable. But we generally consider that we solve that problem where the given function and the initial data is okay. Okay, so now you have to prove this one. So proof is very easy. So what we have given? We have given 12 because UH is solution of this equation. So put VH, V is equal to UH. Here V, because this is for all V belong to VH, so I can choose V is equal to UH in 12 we get. So if you will take this there, so this become UHT. This is the partial derivative of UH with respect to T, and UH plus del UH and equal to F and UH. So I am going there because I need this 12 again and again. So now the second term is okay. That can be written in the norm form because this can be norm of del UH square, and this term can be written as this term UH T, UH can be written as 1 by 2 dy by dt of norm of UH. Okay. Means that this first term can be written in this way, and you will differentiate this, twice will cancel out with this, and UH as this, and again we will derivative with respect to T. Here is because UH is also function of X and T both, so it's behave like a partial derivative. So this become, then this equation become, then say its name, if I am saying this is suppose I am saying star, then star become then star become 1 by 2 dy by dt of norm of h square plus this become del UH square and equal to, so the right hand side I can apply here the Cauchy-Schwarz inequality here. Okay, Cauchy-Schwarz inequality, so then this become less than equal to norm of F, norm of UH. Apply here Cauchy-Schwarz inequality. Okay, yesterday we told you because this is a no inner product, so this is bounded by norm of this and norm of this. Okay, so now multiply by 2 both sides. So this is 2 here, this is 2 here. Now integrate with respect to T with limits 0 to T. So what we get? We get UH square and plus twice time integration 0 to T del of UH square dt, and when you will put here integration, this is cancel out. So this is at the UH at T time and at 0 time, so that will go in the right hand side. So norm of UH of 0 and plus twice time 0 to T norm of F, norm of UH. Okay, so now you can omit this 2 from here because obviously that this term is bigger than this guy and without 2 here, means that UH square plus this integration 0 to T. Okay, so I can say that this you can omit here. Okay, so this is less than equal to this. So this is what? This we have defined the energy norm phi and phi here, and here is U. So you can say triple UH of T is less than equal to norm of UH 0 plus twice time 0 to T norm of F, norm of and dt. Okay, so now you have to prove, but what you have to prove, this. Okay, so this is also a solution, our semi-discrete solution here. So you have to finish this from the right hand side. So you have to do some calculation and you have to do some manipulation. You can say that after some manipulation, this should be out. Okay. So main target is this, to remove this UHT from the right hand side. Okay. So now I'm letting the triple norm, I'm saying triple norm here, this at some point T star is equal to maximum over 0 less than S less than equal to T of triple norm of UH. This is UH. I'm saying what I'm saying that in some interval 0 to T, there is a some point T star where this attain the maximum value over the whole interval. Okay, so now oh, one thing I think so. This is square here. This is square here because this is I have defined the energy norm. I think that should be square here. Energy norm was like this: 555 square is equal to 5 square plus 0 to T and del of 5 norm square ds. So this was the first energy norm. So if I have written here without square, so you can keep it correct. It is square here. Okay. So now one thing you can see in this one, I am taking the maximum for T outside because this is also some particular T is equal to 0. So I am saying that maximum, this guy is the maximum of all this. Okay. So if I am taking the maximum of this and maximum of this, so I can written as triple norm. You can say energy norm is bounded by so UH and obviously that there may be square also because this was square, so integration by part, so this is also square. So if I am taking this is the common, so this is P of 0 here. And plus twice time 0 to T norm of F and ds, and taking this common, so triple of this UH of T star. Because this one term was here, so I am taking maximum of this. So then this is maximum. So also because these are two things. One in because this is square here, so one maximum I am taking outside. So this is equal to this side. So obviously that this is for all this. So you can say that this implies energy norm UH of T star is also, this is bounded by this guy here, and energy norm of T star. So now this is one cancel out, so you can say this implies energy norm of UH T, because obviously that this was maximum, so I can say that this is greater than equal to energy norm of for all T. So this is bounded by norm of UH0, this is UH0, and plus twice time 0 to T norm of Fs and Ts. So this was the first energy norm bound, and we have proved that our semi-discrete solution is bounded by this in form of energy norm. So you can say this is stable here because this is totally dependent upon the initial data and the given function, and these two guys are also the nice guys. Okay, so one more thing also I'm not proving because I have 1 hour. In 1 hour I have to start the differential quadrature method and explain how to apply this one. So I'm just writing the result, second result for this. So theorem 2, the let UH is the solution of semi-discrete problem. Problem 12. Problem 12. Then this result hold. This was, you can say, the previous one. You can say that type of L2 type of norm, because here is the L2 space, but here is the H1 space, and that is equal to norm of del UH of 0 and plus twice time 0 to T f of s square ds and 1 by. So this is the second theorem. It is easy to apply. Here I can define just what is this norm, means second energy norm, you can say the second energy norm. So okay, this is the second energy norm, or you can say the H1 energy norm. Sometimes you can say H1 energy norm. So that is what, that is the second energy norm, that is equal to phi of T square 1, that is equal to norm of phi square plus 0 to T norm of phi of T s square or ds. This is the second energy norm. Means here is derivative with respect to T here. So by defining this energy norm, we can prove that our solution is bounded by these things. So obviously that this is the stable here. So now one more thing I want to give to you here, some name of some books, some well-known books for FEM. So there are 3 books, volume 1, volume 2 and volume 3. That 3 are enough, and these are written by Professor Alexandre Arn, Professor Alexandre and he is some colleague. Alexandre Arn. So first one is what? Approximation and interpolation. And so first book is okay. This gives just about the idea of approximation and interpolation. And second one is Galerkin approximation. Galerkin approximation, elliptic and mixed PDEs. Mixed PDEs, or 3-1 is the time dependent, you can say that. That is the first order and name of this first order, and time dependent. Time dependent PD. So you can see these 3 books, and these are free available over the web page of Professor Alexandre Arn. So these are, I think, from India, Paris. And one more well-known book you can say, you can take here. So that is Suzanne and Brenner. Suzanne C. Brenner. And this is what the mathematical the mathematical theory of finite element method. Theory of finite element method. So these are, you can start with this Hussein and then go, okay, you can start with first one because this is tell you about the approximation and interpolation, and then either you can start the second, then two and third one. So these are some lectures on the finite element method for elliptic and parabolic PDEs. Because time is not allowing me, otherwise we can do the, because this was semi-discretization. After that we can do the error estimate for this one. L2 error or some H1 error. H1 error estimate for the semi-discretization. So now come to the next topic which we have given in my notice board, that elliptic and parabolic PDEs by using finite element method and the differential quadrature method. Actually, differential quadrature method is not too much old like finite element method and finite difference method. So you can say this method is, you can say, young. If you say this, if you will use this word, this is young, because this was start in the last 90s, and it was start in 1972, just as the differential quadrature method. So differential quadrature method. So the short form is the DQM. So actually this was started by Bellman and R.K. Bellman or something and his group. Actually there is a history about this method. Why this start? Actually before that, the people using this finite difference method and finite element method, and these methods are, you can say, lot of theory includes in this method. So there was a demand of engineers that thus they want to do simulation, no theory. So just we want to apply some method and which will give us the very good results. So this was started by Bellman and his group to solve the problem of engineers, because for the simulation purpose. Okay, so initially Bellman and his group, actually what is the basic idea about the differential quadrature method is what? It's like to a to b fx dx. You know, this is the integral method. So this is integral, and we approximate this by quadrature rule. This quadrature comes from here. Quadrature rule. By quadrature rule, we approximate the integral. How? By using some weights and the function's value at some nodes. These are some weights and these are the nodes. And there are many methods in which nodes are in some of them are xi's are given. In some quadrature rule xi's you have to calculate, and obviously lambda is, the weights are always unknown. So these you have to compute, and according to that, according to lambda is and nodes, this become different type of quadrature rule. For example, trapezoidal rule, and Simpson 1/3, Simpson 3/8, Simpson's 1/3 rule, and Simpson 3/8 rule. And there are also quadrature, Gauss quadrature, Gauss Legato, like this. So there are many methods. So this quadrature comes from here. Means that this was used to find the approximate value of the integral here. But this method was used to solve the differential equation. Simple example I am saying, suppose we have this differential equation. So obviously what this method will do, here is written differential quadrature method. If I am relating this method with this one, means that we will approximate the value of the derivatives, and in the linear combination of some weights, and weights, because this is first order derivative, so we will approximate first order derivative in terms of some weights and the function's value at the some nodes. Similarly, second order derivative, third and mth order derivative. Okay, so if we have these weights, so we will put first order derivative, second order derivative in terms of weights and put here. So this become very easy equation, and that is the system of linear equation and solve it. No need to develop of theory, and this is because engineer wants that we need the solution, so how to solve the PD. So I am giving the this was the basic idea how the differential quadrature method come in picture. So there is a Weierstrass theorem. Why this method work? This is a fundamental theorem, Weierstrass theorem. Weierstrass theorem. I am not writing its statement. I am just telling you what is Weierstrass theorem. Weierstrass theorem says that if fx is real valued continuous function and define over some closed interval AB, then that function can be approximated by a polynomial of degree n, because fx is what? This was defined over the closed interval AB, and this was continuous. So we can approximate this by a polynomial. I am saying Pnx. So obviously that this polynomial is approximated here. The same thing here we will apply here over the derivatives also here. So that condition what we need already we have, because u dash, u double dash are enough smooth. So what happens? So Bellman gives some approach. The first what was this? So according to this, means according to quadrature rule, we have to approximate these derivatives. Suppose in term of okay, I write here j equal to 1 to n, and suppose I am saying aij are the weights and u of xj. Here is the difference. Here just alpha is, but I am not discretizing this x. Here u of x, u dash of x is described by xi, and here is I comes from here, j is from this one. Okay, so weights are, these are the weights. Similarly, you can approximate the second derivative. Again, suppose I am saying some other weights. Suppose I am saying b, I, and j, and ux. Okay, so if we have these weights, so just put in the equation. If I am putting this equation here, j is equal to 1 to n, u double dash is what? bij u of xj plus summation j equal to 1 to n, and aij u of xj is equal to, this is also discretized, so this is also f of xi. So what? If we have bij, if we have aij, these are some matrix. So this is one matrix, this is one matrix, so this can be written as, suppose this is B matrix, U is this, and plus A matrix, and this is U is equal to, suppose I am saying this is that. So B plus A U is equal to F, or this is the linear system. No need to make weak form, no need to use finite dimensional space, no need to use the linear combination, just find the weights, put in the equation, you will get the linear system and solve this linear system by any methods. Okay. So the main task in differential quadrature methods is what? To calculate these weights. Okay. So Bellman and his associates give two approaches. Two approaches to solve, to find weights, to find these weights. Okay, but these approaches have some drawbacks. Okay, I will give one by one what are that approaches. So Bellman give first approaches, use some basis to find these weights Aij, and so there was a drawback. When you will n is here what? N is here, suppose this is our one dimensional problem, so these are the nodes x1 up to xn. These are the, means first discretize the domain here. So in first approach, when you will increase number of points, means number of nodes in the domain, so this become ill conditions, so Aij become ill conditions, so solution become unstable here. Okay, in the next approach he used some particular Legendre, its name is Legendre polynomial, and their roots are used as a nodes. Okay, so that's why there was a demand of some general approach which can overcome the drawbacks of these two approaches given by Bellman. So that was given by the Chang-Hsu. That was given by Chang-Hsu, and that is called general approach. Approach to find weight coefficient. To find the weight coefficient in 1991. So you can see that this is not very old method. So first I will explain how to find the weights of first order derivative. So for this I am consider one dimensional problem over the interval a to b, and xi's I equal to 1 to n are nodes, or you can say grid point. Basically this is what? A to B. This is, suppose I am saying x1, this is saying xn, and suppose this is the xi. Okay, let fx is sufficient smooth function on the interval over AB, then their derivative, first order derivative at ith point is approximated by summation j is equal to 1 to n Aij f of xj, and I is also here 1 to n. Okay, so these are the weights. And obviously that these are the unknown weights. So first task is to compute these weights. So for this we will use some basis functions to find these basis some say its name it, so you can say this is one. So what Chang-Hsu used? Chang-Hsu used the the Lagrange interpolation. Use the Lagrange interpolation to find this. So means that he used two type of functions. Function to compute weights that are AIs. Number one is RKX, that is equal to the simple weights x की power k minus 1, k is 1, 2 and here, okay. And second type of weights, second type of functions, you can say bases, are use the Lagrange interpolation. Mainly are Chang's use the Lagrange interpolation. And you know already the Lagrange functions are what? These are defined as mx, x minus xk, m first derivative at the xk. So this is at xk, at the point k here, and again k is equal to 1 to n here. That's fine. So say this is 2, or say this is 3 here, where mx is what? Mx is x minus x1, x minus x2, and so on, x minus xn. These are the bases, and that means what? First order derivative of m at the point xk is written in some product form, p equal to 1 to n, p not equal to the k, and xk minus xp. This is this. Okay, so Chang's use 2 and 3 as basis to compute the weights. Okay, so how to compute this? This is important. If you know that how to compute, then this method become very easy, and it is easy to apply for elliptic as well as parabolic PDEs. Okay, so now I'm driving here and I will compute these weights AIs, which are first order derivative weight coefficient, you can say that. Similarly, we can approximate the second order derivative in the linear combination of some weights and the function's value at some nodes, and again we will find the weights. Okay, and then similarly we can go up to higher order, means mth order derivative weights, and then find. Okay, so now for make this simple, for simplicity, 3 can be written as for simplicity we set you can see we set this can be written as mx is written as n of xk and x minus xk, where with this condition n of xi xj is equal to m dash of xi, and Kronecker delta, where you know that Kronecker delta is what? Ij is equal to 1 and 0 if I is equal to j, if I not equal to j. Means that this was a big product here, x minus x1, x minus x2. So if you cannot differentiate 2-3 times this capital N function. So for simplicity, so we have written this in this way. And what is this guy? This guy is at xi xj become this. You can check that it is easy to add. Mx is equal to this and this. Just leave k and all are here, and k is running from 1 to n. Okay, so now Rk become what? This Rk x become what? M is this n of x minus xk, and this x minus xk, this is also n x minus xk cancel out, or in denominator there is 1 at the xk. So give it its name, I think it's up to 2, so this is 3, and suppose this is 4, so I'm saying this is 5. Okay, till now I think there is nothing too much about like differential like finite element method, because in finite element method we use many basic things of the functional analysis, norm, inner product, Sobolev space, very many things. But here just simple calculation. So that's why this method is easy for the simulation purpose. Okay, so now put 5. Motive is what? Motive is to find these weights. So what I will do? Put 5 in 1. Put 5 in 1. We get, because in the left hand side there is a derivative at xi point. So when I will put here, this is constant thing because this is at point xk. So only its derivative at the point xi. So this become first derivative of, okay, you can write just n dash. First derivative at x point k divided by m dash xk is equal to summation, and j is running from 1 to n. ai, j are the weights, and the in place of f I am writing this rk is defined by this one. So this at the point xj, xk, and divided by m1 and xk. Okay, so if you want to cancel out this become, because both are the constant. Fine. So now see here the properties of this capital N. When these two guys xi and xi, I and j are equal, so its value is just m1 xi, otherwise 0. So when you will run this j is equal to 1 to n, and then this k becomes j, or j become k, in that case its value is 1, otherwise this become 0 here. So when k is equal to j, or you can say j is equal to k, so this become n1 of xi, xj, because I am taking k is equal to j here, and that is equal to, and its value become this m dash xi and aij, and m dash of xj. So this means aij is equal to this first derivative. Okay, you want to write first derivative at the point xi xj, and divided by first derivative of m at xj. So we have this one. Say this number 6. Okay. So now because this is number 6 aij we have, now we need the value of this guy. From where? From here. Because when you will differentiate this guy, now equation number 4, m time, so differentiate 4 m times, we have mth derivative of this is equal to what? this will be mth derivative of this guy and x minus xk as it is, and plus m here and m minus 1 derivative at the point xk. Okay, so means that its value you can compute from here. Means I need this n1. This is okay, this we have already, and that is this. So it is easy to compute in MATLAB or any software. So because this is xk's we have, so we can find this product easy. Okay, so now I will put, because I need n1, so I will put m is equal to 1. So you can say give its name is 7. So put m is equal to 1 in 7. So what we get? And you have to find the value of this at xi, xj. So what you will get? You will get n1 of xi, xj, that is equal to m1 of xi divided by xi minus xj, and I is not equal to j, because I is not equal to j. Otherwise this become 0 and this become infinite. So this is the value of n1 does. Okay, so now put this one, so it is 7, put 7 in 6, put 7 in 6 here. So what we get? We get aij is equal to m1 of xi and xi minus xj, and in denominator already there m1 and xj when I not equal to j. So these are the weights when I not equal to j. But you know that if I equal to j, what will be weights? Okay, so you will say that when I equal to j, so we can do some more computation and you can find. Okay, so because for I equal to j, from here we cannot compute the, because when you will put xi, xj, both are equal, so this term becomes 0. So from here we cannot compute the value of n1 this. So means that from this equation, sixth equation, we can only compute this one. Means that when I not equal to j. Okay, so now we will try, because when you will put m is equal to 2 here, so here you will get n1, and let's see what we'll get for m equal to 2. So for m equal to 2, there will be some problem, and we cannot use these basis function to compute the weights when I equal to 0. So put here in 7, use m is equal to 2. What we will get? M2 x is equal to n2 x xk, x minus xk plus twice time n1 of x xk. Okay, but what we need this thing, xi, means that these weights for I not equal to j already we have, but we need when I equal to j. You can see that we have, this is a matrix, aii, a11, a12, a1n, a21, a22, a2n, and so on. So means that we have these weights, but we have to compute the diagonal weights. Okay, so when I put this here, so when I equal to j is equal to k here, so what will we get? We get this become m2 xi, and because this become I, so this becomes 0, or that is equal to twice time n1 of xi. So this imply n1 of xi is equal to second derivative of this at xi and divided by 2. Okay, so we can find aii in term of this, or that is equal to, if I am using 6 here, so put in 6, so m2 xi divided by 2 and m1 of xj. Okay, both are same, so this is it. But what is the problem here? There is a but here, because to compute this second derivative of this capital M is not easy task. Okay, because these are what? These are multiplication of n linear polynomials, x minus x1, this is polynomial n time multiply. But problem is what? When you will increase number of points, n is equal to, suppose I am taking 100 or 200. So what will happen? Then to multiply, to find its first derivative, then second order derivative, and then put this point xi, and then compute. This is very difficult. Okay, so this way of computing aii is the bad way. So that's why we will use the another basis which I have told, rkx is equal to x ki power k minus 1, k is equal to 1 to n. I will use these bases. Yeah, you can say Chang Shu use these bases. Okay, and just we use just k is equal to 4, 1, k equal to 1. So r1 x function is this is one constant, and what we have to find out, xi is equal to some j is equal to 1 to n aij f of xj. He used arcx is equal to just 1. When you will put 1 here, so this becomes 0, and summation j is equal to 1 to n aij, and this is 1. So means that summation of this is equal to 0. So I is also running from 1 to n. So yes, from here he computed minus this j equal to 1 to n aij, and j not equal to I. So these are the weights which are very easy to compute, because you can see that the diagonal element can be computed with the help of this. Means first element can be computed sum of all these and minus of this. Okay, so this is a very good idea, because this makes this matrix diagonally dominant also, because the diagonal element are the sum of all element in that row. Okay, so this become diagonally dominant matrix. So now similarly in this way, so finally what we have? Finally we have the weight coefficient of first order. So what are that? These are the weights. Yeah. So this is for I not equal to j, and at ii is equal to minus summation j is equal to 1 to n aij, and j is equal to this. So these are the weights here. Okay, fine. So we got the weights of first order derivative. So similarly, we can again approximate the, because suppose most of the problems for the are in second order OD or second order PD in space. So at least we have to find the weights of up to second order. But if you have to solve the PD of higher order, then you have to compute the weights of higher order. Means, but generally people are interested in second order and fourth order by harmonic. So up to fourth order, that is okay. So again, weights of second order. Second order derivative. So here, suppose I am saying that the second order derivative at the xi is approximated by j is equal to 1 to n. I am saying the name bij and f of xj, here I is also 1 to n. Okay, so the same procedure we will do. We will put rkx in this equation. So his name was here I have written 13. So put this rk is that is in form of xk and divided by m1 of at the point xk. Yeah. And this was first basis. Second basis was just rkx is equal to just only xk minus 1. These two bases. Okay. So use first basis. Put here. Okay. And this becomes the second order derivative here at the point xi xk divided by at this point, and that is equal to summation j equal to 1 to n bij and n of xj xk divided by m1 of xk. So this is cancelled out. Again the same thing, when k is equal to j or j equal to k, so from here this implies bij is equal to second derivative at the point xi and xj and divided by first derivative of this and this. Say this is 14. Okay, again from equation number 7, from we have to find this second derivative. Okay, so from 7, I am saying from 7, just calculating second derivative at xi xj, that is equal to second derivative at xi minus twice time n1 of and this and divided by xi minus xj when I not equal to 0. Okay, so put this here. One thing I want to tell you that I have in previous one I have computed aii is equal to m2 of xi divided by 2. This is very important here because this come here m2 second derivative of m at the point xi, and I told you that this is very difficult to compute. So if I will put the value of capital N2 in these weights, so this guy is there, so this guy should be replaced by that one. So that is equal to, this value is equal to twice time aii minus twice time n1 of xi xj or divided by xi minus xj, I is multiplication. Now put this here and the value of NO1. So finally what we got, Bij is equal to, so okay, I'm writing there. So we got Bij is equal to, just a minute, Bij is equal to twice time, and I will use the definition of this one because Aij is what? This value. So this value I will use as, because this will also come in Bij, so I will replace this by Aij. So finally what we got, 2 Aij Ai minus 1 upon Xi minus Xj when I not equal to j, and the same thing as here. So Bi is equal to minus summation of j equal to 1 to 1 and Bij j not equal to 0. So these are weights of first order, these are weights of second order derivative. Okay, so now come to the point. Similarly, we can find the derivative of weight coefficient of higher order derivative, and these derivatives, if you have just you can, if you will think about computation point of view, so Aij can be computed. Just find this, and this is already. So this is matrix. If you have when I not equal to j, so this can be computed. Just I equal to, just apply 2 for loop, say that j not equal to I, and sum of all these and put minus here. So this is easy to. Similarly, if because we have Aij, so you can use this Aij here directly. Ai here, x minus x. So if we have Aij, then it is easy to compute the Bij also. Okay. So similarly, you can go for the higher order. So I am writing the weight coefficient of mth order. Mth order means if I am saying Wij, I am saying the weights of mth order derivative. So these are what? These are equal to m. Inside is Aij, Wii, m minus 1 and minus Wij, m minus 1 Xi minus Xj when I not equal to j, and for I when I is equal to I, so in that case this become Wii equal to minus summation j is equal to 1 to n, j not equal to I, and Wij of m. So this is the weights for mth order derivative. If you have first order, you can compute any order with the help of this one. Okay, see here, just a minute. Oh, that's fine. Yeah, this is okay. This is inside, because when you will put m is equal to 2 here, so 2 here, Aij here, 1 here, Aii 1, and this is 1 here. So Aij become at first level it is okay. So this will common and 2 Aij, and this is fine. Yeah, this is okay. Okay, so now this was one way, but if you have the first order weights, so we can compute with another way also. How? Because if you have the weights of first order, then and you have to find the second order weights, so means that we know that this can be written as d of dx of df of dx. Understand? Means this second derivative we can write like this. And if you have to find the, because now apply here the weights here, means that you can say second order derivative, you can write summation j is equal to 1 to n AI, suppose I'm saying K here, okay, and Fk dash at xk point. I put this. Understand? Means that if you are writing this as, so this guy can written as, just apply here this, think about, suppose this is a G here, okay, G is what? G is the first order derivative of this f. Okay, when you will apply first order derivative over here, so weight coefficient will be aik, and here you can say this is just g of xk. Okay, and this g of xk is nothing. Okay, it's k. Aik. This g of nothing is, this is the f dash of at xk. Again apply this in term of this k is equal to 1 to n aik, and this is again summation j is equal to 1 to n akj and f of x. You can say this. You can write in the reverse way. So you can say that this summation take outside, one summation is outside and one summation is outside. So you can say finally, means if you want to find this bij, that is nothing, aik ak, means multiplication of first order weights. Suppose I am saying that a is the first order weights of first order, so just to find the second order weights, just multiply these two. Okay, this is also a one way, but I am saying this is a one, but this procedure become costly here. See that we have already these weights bij is equal to this one, and you will see that here round of error and computational cost will be very low as compared to this multiplication. Okay, here will be n cross n, two matrix, and we have to multiply them. So here round of error will increase as n goes to infinity. So that's why people don't use this way to compute the high order weights. They use these two. Okay. So now we have the weights now. Now come to the picture and the how to solve this, any PDE or ODE by using differential product. Okay. So I'm first give example how to solve ODE, yeah, first order or second order or third order, what you like. Okay, because we have the mth order weights we have. So first we will do what we will do as a simulation purpose. I am explaining here. Just in some software, define number of points. Suppose I am saying define 10. Okay. So find xi is here. Xi is for your interval is 0 to 1. So xi you can find xi upon this, and I is equal to minus 1 here. Because this is minus 1, I is equal to 0 up to n minus 1, so you will get the all n points here. If you want to start this just 1, so I minus 1, and this will go up to n, all this is okay. No, this is minus 1. Because the first element should be 0, so last element should be 1, so this comes. Okay, then compute Aij with the help of this formula, then compute Bij with the help of that formula. If you want to solve just second order, for example, I am taking an example, solve y double dash plus y is equal to fx with the initial condition, with boundary condition both are 0 and x belong to 0 to 1. Okay. So obviously we have Aij, we have already computed. Now discretize, say its name is 1, say it's 2, discretize 1 at x is equal to xi, so this become what? Y double dash xi plus y of xi equal to y of f of xi here. So now its value comes from the differential quadrature method. Now apply differential quadrature method. So what will this say? This will give at xi, that is equal to summation j is equal to 1 to 1, which we have done recently, and this only one derivative is there, so no need to go first order and higher order. So only just approximate this. So put this, say this is 3, say 4, put 4 in 3, so we get summation j is equal to 1 to n, and bij, yj. I'm saying just for simplicity, this is y of xj as yj, and plus, suppose this is yi, so I'm saying this is yi and is equal to of fi. Okay, so now make it system. System is very easy. This become b11, b12, b1n, bn1, bnn. Here will be y1, y2, yn plus. This will come just in diagonal. This coefficient 1, 1, 1. This will 1, 1, 1, and 1 diagonal, and here will be y1, y2, and y1. So all element will be 0. So or you can say this implies this will become b11 plus 1, b12 and so on, b21 and b22 plus 1 and bn plus 1, and outside I am taking outside this y1, y2, y1, y2, yn, and is equal to, in the right hand side I am saying that this is f1, this is f2, and this is f1. Okay, now apply the boundary condition. What is given here? y1 is 0 and yn is also 0. So y1 is 0, yn is 0 already given. So you can leave this to make it solvable. So finally you will see this matrix. Leave first row, last row, first column, second column, and here will be y2 and yn minus 1 is equal to f2 and fn minus 1, and solve the system. So this was procedure how to solve the second order. Okay, this was first order equation, second, and this is easy. Now come to the time dependent problem. For example, in finite element method I explained the heat equation. Consider here this just heat equation minus uxx is equal to, suppose I am saying this fx. As I told you here that in finite element method also we are applying the differential quadrature method in space only. Okay, so here first, because here is the two element, one is x, one is t, so first discretize in time. So that is called, you can say, semi discretization in time. Okay, so this is first step. That is what, suppose I am writing using here the finite difference method, suppose forward one, or you can use backward one also. So I will say n plus 1 minus u of x tn divided by delta t. Delta t is the step length in the t direction, and minus here either you can use Craig-Nicholson or you can leave as it is also. Suppose I am using Craig-Nicholson for the for this one. So u of x, okay, xx tn plus 1, and okay, I am just saying this is just don't use Craig-Nicholson also. For this is unknown here. and is equal to f of x. So simplifying this one, this means or you can say, or you can use, or u of, say this is u of n. For simplicity, say this is u of n. So unknown is what? Unknown is n plus 1. So you can write this n plus 1 and this delta t multiply here, delta t uxx n plus 1, and this guy will go that side because this is the known thing, u of n and plus delta t f of x. Now you can see that for each n, this become, we have a system of ODE of second order. Because these discretize here, this partial derivative become the derivative, simple derivative in just x. Okay. So now approximate the derivative term with the help of differential quadrature method. Means that here is the this term is what? Xx at xi. This is simplified. J is equal to 1 to n, bij, and un plus 1 of, or you can say some name also for simplicity. I will say this is you can say, and say, okay, I'm saying, say here, say un plus 1, this is equal to capital U. So this become u of xx at xi is equal to j equal to 1 to n, bij, u of n. Now put this here and same discretize, because this is system of OD, so you know already how to solve by previous example. So this become ui, capital Ui, sorry, because I have given name here, capital Ui minus delta t and summation j is equal to 1 to n, bij, uj, and that is equal to ui of n and plus delta t f of I. So this become one matrix and uj is outside. This is column vector here, and you know that when n is equal to 0, this guy comes from the initial condition. Obviously that this had some initial condition, suppose gx, and u is equal to suppose 0 on the boundary here. So you can see that this become a matrix, this is a vector, a known vector, and this is also a vector. So you can solve this. So, but you have to solve this at every time step. Okay. So decide delta t, and during the simulation do its process. And this was the last lecture. So thank you very much for listening me. If you want to see differential quadrature method, there is a book by Chang Hsu for on the differential quadrature method. So you can find this book and all the details are there. So people have solved different type of problems by using differential quadrature method, even though Navier-Stokes equation and many more problems. So again, I want to just say thank you very much for listening me, and again thank you to ICTP and SIMPA to give me chance to deliver my work or my research area at this platform, and also thankful to Professor Andrea Kangyani at CISA who collaborate with me and do some good work on finite element method. So thank you very much. Thank you.